Hi everybody, this is Brian. Today we're going to be looking at paired data in StatPowers, specifically two dependent variables, correlation and simple linear regression. This is going to be all handled in one page in StatPowers. This is the two dependent parentheses paired samples. Paired data is usually more like two samples where the observed individuals are observed maybe before and after some treatment, or maybe you have twins or something like that. Two samples where individuals are paired between the two samples. That's a little different, although some of the analysis is similar. We're going to be looking at two variables, two quantitative variables, and the relationship between those two variables, as opposed to one variable that's measured in two samples and they're paired individuals. Okay? So here's a simple example. It doesn't even have any context. Based on the data below, we want to calculate a regression line and to two decimal places. Now we've got X variable and Y variable. We don't even know what X and Y are. But I'm going to just show you how we do this analysis. In StatPowers, basically we're going to just copy the table and paste it over here. Click calculate now, and then it's calculated. What's calculated is, so the stuff that we're going to be looking at are going to be found in the correlation estimation. First of all, I'm going to open this up. So this is calculating Pearson's correlation coefficient, the most commonly used correlation coefficient. And this is, remember, a correlation coefficient is going to be some measurement of how related, what the linear relationship between two quantitative variables. And it ranges from -1 to +1. Negative 0.986 is a very, very strong negative correlation. And it also gives you a 95% confidence interval, and we can change the confidence level by just cycling through, changing the value here. You can see how that updates it. The next piece is a test for correlation. You can open that up. The correlation test is, traditionally we're interested really whether or not the correlation is equal to 0, which is to say the null hypothesis states that there is no correlation, or sorry, there is no significant linear relationship between the two variables. And the alternative hypothesis is that there is a significant linear relationship. And that translates into correlation equals 0 versus correlation not equal 0. Typically for an intro stats course, we'll be using the T transformation. The Fisher's Z transformation can be used for large samples. But here we have a very, very strong correlation. It's no surprise the p-value gets rounded to 0. I'm going to go up. I'm going to change the position to 6 decimal places just to see. Oh, it still rounds to 0. Gives a rejection region also. Any correlation beyond 0.5759 would be considered significant. I could change the significance level, of course, to something smaller. I could change it to 0.001, but even at this very, very, very strict significance level, this is a significant correlation. Okay, so these are just a couple of things on correlation that you can do. I'm going to close this and I'm going to move down to the charts. The hex plot is a very fun plot. It's very, well, for a data set like this, it looks basically like a scatter plot with hexagons. But the benefit of hex plot is if you have a lot of data and the dots just kind of overlap each other, the darkness of the hexagon bins is going to correspond with how many points are in each little bin. So it's a little bit like a histogram meets a scatter plot, and they have a baby, and the babies are all hexagons. And you can change the size of the bins, and you can see for this small amount of data, only one of those hexagon bins has more than one observation in it, so that's darker than the others. But anyway, you can also turn on marginal distribution, so you can look at and see what the those are going to be like kind of histograms for the X and the Y variable. So that's a nice little plot, tells you a lot of information, and it's pretty concise. The next one I'm going to look at is the scatter plot, your standard scatter plot. You have a couple of options here. You can show the trend line, which is the line of best fit. You can show confidence interval bands. This is a confidence interval for the mean. So we're 90, you set the confidence level up above. So this confidence level is set at the moment at 91%. I'll change that to 95%. And you'll see that the band's actually a little bit wider. It's kind of hard to see. Let's see if I can have those both open at the same time. All right, I'm going to just, I'm going to change the confidence level. Yep, you can see to 95. Okay. Yep, here we go. So this is a confidence band for the mean. So for any value of X, we're 95% confident that the mean value of Y would be between those two upper and lower bounds. The prediction interval band is going to be wider, and if we're predicting new values of Y for any value of X, we're 95% confident that the values of Y are going to fall within the blue area. Okay, so it's a nice visual. You can turn those on, turn them off. Then finally, I'm going to go to simple linear regression next, and I'm going to actually change my precision to 3 decimal places. It's going to make the output look a little bit better. So what do we have? We've got standard regression statistics. You've got the regression equation, which gives you so for simple linear regression, the regression equation is, the prediction is the intercept plus or minus a slope times X. And if you change the names of these variables, if I change the X variable to, let's say hours, and Y was score, like you're predicting your score, let's maybe not something that would be bad. Let's hours, let's say hours video games, and test score. Let's imagine that the more hours of video games someone plays, the lower their test score is. I'm going to recalculate, and then it'll refresh the linear regression statistics. You can see it names the variables in here according to the variable names that you've picked. So here we see that there's a decrease of, for every 1 hour of video games, the on average test score is going to decrease by 1.088 points, I guess. The multiple R is also known as Pearson's correlation coefficient, which we looked at above. The R squared is literally, you take the multiple R value, or Pearson's correlation coefficient, and you square it, and that's the R squared. Adjusted R squared, I'm not going to get into right now, but it's given here. Standard error is, roughly speaking, it's the standard deviation of the residuals, and the residuals being the difference between each actual Y value and the predicted Y value from the regression equation. Take all those residuals, and the standard deviation of that is known as standard error. The ANOVA output is essentially just telling you how significant of a, like how well, put it in this way, how significant is the linear relationship. That's really, and it's actually the exact same output as a hypothesis test. But the significance level here is exact same as the p-value of the significance of the significance test for correlation, whether the correlation equals 0 or not. But it's calculated using an F statistic, which is more general and applies to multiple linear regression as well. That being said, I'm not going to get too much into it, but it's there. You'll look at this much more, this ANOVA output, much more for multiple regression. And finally, down below, you've got some other statistics for your output, for your regression. You've got for each of these, for the coefficients, the intercept and the coefficient for hours, You've got a standard error for that and the corresponding t-statistic and a corresponding p-value. This will allow you to see whether any of these estimates are, or these coefficients are significant or not. It may be that the intercept has, usually if the intercept is close-ish to 0, its p-value is going to be rather large. Like it might not be significant, but we usually don't worry too much about that. It's really, we're concerned with whether the p-value for the slope coefficient is significant or not. And lastly, you have the option for predictions for x. So if I was interested, what would be the prediction for somebody who played, say, 12 hours of video games? I hit enter, I'm going to scroll down a little bit, and it tells me I predict a test score of 19.857 for that amount of video game hours. And also I get two intervals, a 95% prediction interval for test score, which the 95% is affected by my confidence level. If I change that to a different, if I changed it to 96%, 97%, you can see all of these confidence intervals are all using the exact same source for their confidence level up above. So anyway, the prediction interval, that would correspond to that blue band in the scatter plot, and then the prediction interval for the mean test score, that's corresponding with the dotted line band. So we would say, if somebody plays 12 hours of video games, I'm 95% sure that they're going to get a test score between 18.242 and 21.472. That's for any one individual person, right? But instead, if I asked, what's the average test score for people who play 12 hours of video games? Well, I'm 95% sure the average test score for those people would be between 19.372 and 20.342. So when I'm predicting for the average of all of the population, that's a tighter bound. But if I'm predicting for one individual, that's going to be a wider bound. The reason is there's two sources of uncertainty. One is I'm a little bit uncertain about exactly where the mean is. And secondly, there's this additional uncertainty with basically the variation from individual to individual. So I'm going to go back up to the last plot, which is a residual plot, which is going to be very straightforward here. It's just plotting for each x value, I plot its residual, which is the difference between the actual y value and the predicted y value that you get from the regression equation. And those are plotted, and this horizontal line is the line at 0. And the things you want to look at for the residual plot, of course, is you don't want to have any sort of discernible pattern. It should have about the same amount of variability across the board. That the spread, the vertical spread of these dots shouldn't depend on the x value, and that's what you call homoscedasticity, when the kind of the randomness is equal across the board. And you don't want to have any sort of shape or pattern, like a curve or something like that. And anyway, so that's an overview of what you have for this. I'll show you just what this stuff would look like for a much larger data set, and we'll see a couple of differences there. So I'm going to fade into that. Okay. So here I've got another data set. This is the length and weight of a bunch of giant African giant snails, and I'm not sure if this is simulated or what. But anyway, so what I want to look at here, I'm going to look at a couple of the same things. I'm going to look at the scatter plot first, and then compare that to the hex bin plot. So I'm going to actually close the data entry and open up the scatter plot. So here you can see that there's a different kind of a shape to this data. It actually looks like it's got a bit of a curve to it. And it might be kind of hard to see, but here you can really see there's a large data set. There's about 1,000 individuals. And it's hard to see just how dense these are because the dots overlap each other. So the hex bin plot is going to have some advantages over the scatter plot here. Here I've actually set the resolution to 40. You can see as I change the resolution, the image, you've got a little bit of a change to the this hex bin plot, but you really are getting a nice picture of how the density of these points in this area here, and then there's a couple over here and here. And the marginal distributions tell a nice story here also. You can really see for the length, this is the distribution of lengths. There's a few little outliers over there. And for weight, this is the distribution. And here's a couple of the outlying individuals for weight. So you can see that the hex plot is going to be a little bit more useful for large data sets. For smaller data sets, it doesn't really have that much of an advantage. But it does tell you, it does give you a nice snapshot of the data of the two variables and how they're related with each other. And I think that's the main thing I wanted to talk about. So this is so for dependent variables, for the correlation for simple linear regression, it's a good overview of what StatPowers can do for you. All right.